time here. So as I said in class last time, I'm going to have a quiz posted for you this afternoon. It's not ready yet, but it's there. It's getting there. And I will check it by seeing that you have it and that you worked on it on Friday. Just walking through. Yes?
Are we working on it in class on Friday?
No.
No, so have it done prior to
Yes.
class.
Yes. Good. I'm glad you clarified that detail. That was in. So yes, I want you to work on it between Wednesday and Friday, and then I will check it on Friday. Again, today we are going to talk about Wiggly Channels, because as it turns out, straight ones aren't really stable. And the wiggly part leads to meandering. This is fake. I made this on a silicon graphics machine in 1996, 7, something like that. I can't make an animation that's not that nice anymore. The silicon graphics isn't the thing anymore. Those are the ones they used to make Jurassic Park. Yeah, and it was only like in the last year or so that I found a video format converter to go from the silicon graphics video format to MPEG or MP4 or whatever. So I've had like a little bitty version. This is like the full Monty. And it's kind of nice for illustrating a few things that we will talk about. In particular, this is just a really simple case. While it looks like there's sediment, there's not. It's fake. But there's not really even meant to be sediment so much as just the river is staying in the same place and the rest of the topography coming up around it. And then the color map is according to the color map of the topography that is according to elevation. So the very deep stuff, you know, the lowest stuff is blue, and then it, you know, it's sort of. I mean, I worked for hours on that color map, so hope you appreciate that. But one of the things that this kind of illustrates is that in a place where a river has been migrating, you can have old river elevations in that landscape that, and where those seem coherent enough, we call them strath terraces in the case where they're erosional. But I'll get to that. I should stop getting ahead of myself and get with the program. All right. So I want to start off just with I don't know. This is starting with a picture of the Hocking River in Athens, Ohio. I spent a fair amount of time there in my 20s. There's a friend of mine went to school, University of OU, whatever. And I just remember driving by this river and noticing, you know, it's like so sad that they had straightened it and that it just wouldn't stay straight. Because straight rivers, at least if they've got any kind of sediment load whatsoever, that is a bed load sediment load, that they just don't stay straight. They form bars. You know, the sediment tends to be kind of carried down the middle of the channel, but then it also tends to start depositing there or nearabouts. And if you get just a slight asymmetry, a little perturbation in where that, you know, which side of the hump in the middle that sediment might be depositing on, you start building a bar on one side and pushing flow to the other side. And hence you start developing in this case, I wouldn't necessarily call it a meandering pattern, but you start to get bar formation, point bar formation, and erosion of the opposite bank. And pretty much any river that has a substantial sediment load with which to form bars does this. And the variety of forms that we get from it is due to other sorts of details. So let's talk a bit about that. First, let's look at how partly how the bar development feeds back to leading to bank opposite erosion of that opposite bank. This is Muddy Creek in Wyoming, and just really intensively studied in the 80s. You can see the contours of elevation with arbitrary datum. The 10 centimeter contours, which is friggin' awesome. That was way before LiDAR or anything like that. That was all hand surveyed. And then we've got these cross sections. 12 is this one, 19B is this one, and 22 is this one. So as we go through this bend, we start at the crossover point, which is essentially where we're at a place. That crossover is essentially where the curvature, the planform curvature goes to 0. And we can see that the channel is pretty much rectangular at that point, although the highest velocity of flow is hugging this right bank, sort of, because that's where it was at coming out of this bit. So it enters here, and we see by this time the bed has become transversely sloped. We've got a point bar building here, and the high velocity, what we call the high velocity core, if you will, is on its way to the other side, but it hasn't gotten there, even though, you know, it's very steep, but it kind of has to go there because, in part, you know, simply the formation of that point bar displaces the flow, but there also sets up a helical kind of thing, which is a rectangular channel will have kind of two helices like these, but in a lopsided channel like this, the right-hand side one gets very small and it's dominated by the one in the pool. And that tends to make the higher velocity flow also go towards the outside bank. And then you see by the time we're at section 22 here, we've got 70 centimeters per second right up against the bank. And, you know, sure enough, that's also where we see, you know, steepened bank, and it looks like there's probably active erosion of that bank going on. So that slight instability that we start building a bar, and if there's like any perturbation as to whether it's on sort of one side of the middle of the channel or the other, we start building that bar that's lopsided, and that develops a whole feedback that starts driving the flow into the opposite bank and eroding that bank, and then before you know it, we've got a laterally migrating river. So they kind of all do that. I mean, not like I said, any stream that's carrying a significant or substantial bed load is going to form bars, and you'll get this sort of bar building, point bar building, and opposite bank erosion. Now, what happens next is, I think, kind of interesting. So here is a photo of the Ellis River in northwestern Maine. Like the maps of the map on the wall in the house that I was staying in when I was visiting this place, and part of the map was just blank north of a certain point. It's just like private land, don't map it. Anyway, so this is northwestern Maine, and this beautiful little meandering stream coming down probably what looks like a formerly glaciated valley. What you see here is a relatively new and fresh, at least, especially at low flow, exposed sandy point bar. So this is a sand-bedded stream, and it's something that we don't really see out here, but we've got this sand-bedded stream, and one of the things I really wanted to point out to you was all this, photo's kind of low resolution, but all this shrubby, stemmy, rough vegetation here. And here we are at a higher flow in a different season. I've got the red arrows pointing to the two trees that are the same in each photo. And here you can see still that stemmy vegetation, although that sandy part of the point bar is submerged. So this is a banked full flow, but one of the reasons that I show this is that you can see that if the flow gets any higher and starts going over bank, that flow at the edge is immediately going to have to contend with this really rough high stem density vegetation, and it's going to start dropping a lot of sediment, and hence we're probably, well, I mean, what I in fact saw at this spot is that has formed a ridge in what we call ridge and swale topography on the floodplain. Now, all right, so here, that picture was taken from, those pictures were taken from about here, looking at this point bar here, maybe probably more taken from over here, looking at the point bar here. The white, by the way, is the most recent. This is a channel, okay, back up. This is also the Ellis River in Maine. Air photos from 1943, 65, and 90-something. And there's an 86 under there somewhere too. Now, the 1941, that apparent huge wide channel that seems to have later shrunken is simply glare off of the reflection of the sun off of the water. So that's not real. But the topo map was based on the 1965 plan form, and I went there looking at all these bends and trying to figure out where we were, and I was very confused until I finally figured out that bend was cut off. So you've got these bends that are migrating downstream. This is a pretty cool spot here because you've had, due to this cutoff, it's created this small bend, and those small bends for meandering rivers tend to migrate relatively quickly. And you can see that it's sort of knocked into all the other bends, created sort of a cascade of downstream, relatively rapid downstream migration. It's something you could, if you were paying attention, and I'd show you again maybe, you can see in the model animation as well. But what it's done is created a lot of nice fresh sandy bars that have then been colonized by that rough stemmy vegetation that then accumulates lots of sand and creates a ridge. That is that ridge right there. So we're now looking at a cross section of the transect across this bend here. And I have the arrow pointing upstream because just the way I surveyed it, it goes from 0 distance to larger distance that way. But then I went ahead and flipped it on there. So that's why things are backwards. Okay, so we've got upstream end, downstream end. So what happens as the flow leaves the channel? Because you could see, this isn't a river that is shy about flooding. I mean, this is bankful flow. This is like might have been the first, the first 2 times I was there, it was like at bankful. So what happens when the flow goes over bank? Well, it's a relatively low gradient stream. You can see how much migration, that is point bar formation and erosion of the opposite bank, that's occurred relatively slowly over a half century. That is, we're going from 1943 to 1994 or something like that, or 92. So in the course of that roughly half century, 50 years, we've moved maybe a channel width, at least at that particular spot. So it's relatively slow. That means that, and even when it's relatively rapid, you've got a relatively vivacious ecosystem to grow that stemmy rough vegetation. And so when flow goes over bank, it's not all that strong. It's not carrying a whole lot of coarse stuff. It's not carrying a huge sediment load in the first place. And there's lots of vegetation on the floodplain. Because it's going so slow, vegetation always has a chance, almost always has a chance to colonize before anything dramatic happens. And so you get overbank deposition of fines, right? As the flow leaves the channel, it's tooling along like, if we look back here, it's tooling along real happy, carrying lots of stuff in this main channel, and then if it goes overbank, what's it going to see immediately? It's going to see an immediate drop in its depth. It's going to get slowed down by all that vegetation, and it's going to start dropping sediment. And so now it's going to tend to drop the coarsest stuff first and then start dropping finer stuff on top of whatever point bar has been rolling along. Like I said, here's the downstream end and the relatively recent bar formation that's been colonized by the rough vegetation, and is so here the numbers, lower numbers are coarser sediment, lighter shades are coarser, the darker shades and higher numbers are finer sediment. So we see some relatively coarse stuff right up here, but it is kind of on top of some fine stuff. Maybe what you'd expect to get a little variation as as you get different sorts of floods that are coming over bank, it might be dropping different amounts of sediment. A big flood, would have enough oomph to carry a little sand with it. But then all through here, you're mostly getting very fine stuff deposited until you get over here, where this deposition is really most likely just due to flow spreading out onto that rough point bar surface on that downstream end. And so we get a couple of things that happen. All right, let me go back to this. We get a couple interesting things. We get transverse sorting. The coarsest sediment is going to tend to ride along in the deepest part of the pool, and the finest sediment is going to tend to get sort of swept up onto the point bar. And so laterally, it's going to be finer on the inside of the bend, coarser on the outside of the bend. But since the bed is sloped like that, that translates to also essentially a vertical sorting. So as that bar moves along, it's leaving behind what you call a bottom set deposit. It's accreting laterally, coarse stuff down here, fine stuff over here. But if I dig a trench in that, if I go take a backhoe in here, somehow get there and trench that, I'm going to see in my column, in my stratigraphic column, you can see the coarsest stuff at the bottom. It's going to be fining up and if my trench goes out in here somewhere, I'm going to get fine sediment on top of that. So that's known as a top set. Here's a bank on the Willamette, former graduate student for scale. You can't really see the fining upward sequence in this gravel down here because below about this point, you're just dealing with a bank failure type. It's all uncemented, unconsolidated, non-cohesive sediment, so you've just got a slope kind of at the angle of repose there. So there's not enough of that gravel part to really see the fining upward sequence. But you can get that really interesting. Guess I forgot to turn off YouTube. I mean, really? Just so this is I guess this is just the nicest picture I have that shows just such a really clear distinction between that bottom set, which is what you might call a channel lag deposit or channel bed load deposits down here, and then overbank deposits of stuff that probably was carried in suspension, because in order to be carried outside the channel, it had to be relatively high in the water column in the first place because it's overbanked. Now, in a place like, here's some more pictures of the Ellis River in Maine. Very low gradient river, carrying relatively fine sediment, and not a huge amount of it. So things are happening relatively slowly. Again, vegetation has a chance to colonize. These bar surfaces, or these floodplain surfaces, have a lot of strength relative to the sorts of shear stresses they're experiencing as flows go over bank. And in this case, I'm gesturing the wrong way because downstream is left. Now, I did actually walk out along this, and there were places where you could see that flow had scoured out little holes and there were roots stretched tight across them. So the tree roots and such are doing their job. Now, at this particular point, when does it actually cut off? Well, it actually cuts off when a tree falls in on this side and a tree falls in on this side. And the neck there is only the width of 2 tree roots of the trees. This was back in the 90s. I'm sure it's well on its way to being fully in the main channel by now. Here you can see a higher sort of bank full flow that I believe I believe here we're standing over here looking upstream and we can see the water coming towards us through that cutoff. So again, we've got a meandering stream. Again, all streams do this, carrying their bed load, creating point bars, eroding the opposite bank. If the flow is relatively weak compared to the strength of the banks and the floodplain surface, then we get at that end memberist, sort of weakest flow per strongest material or surface. We get the single-threaded meandering stream where those bends don't cut off until they literally touch, until the limbs of them cut off and touch one another essentially. Now on the other end, we've got something like this. This is, I want to say the Chatina River. I know this is the Kennecott Glacier. You've seen pictures of this before up in Alaska, and this outwash carrying a friggin' A-load of sediment, right? Lots of flow, lots of sediment, short growing season up in Alaska. Plenty of green, but stuff's not going to grow fast enough versus the rate at which point bars are accreting in that particular case. So again, all rivers do the same thing, right? It's building point bars, it's eroding the opposite bank, but it's doing it really quickly because it's got a lot of sediment in it. Plus the growing season's short, so vegetation doesn't get a chance to become established on these point bars. So any flow that goes over bank, well, let's think about this. We talked about the flow leaving the channel. What about when it comes back in? All of a sudden it's seeing a waterfall, right? It's seeing a drop. It's seeing a huge hydraulic, wow, I get to plunge back down into the channel. If that material over which it's flowing back in is not cohesive at all, doesn't have much strength to it relative to the power of that overbank flow, then it's going to tend to initiate a nick point. It's going to zip back up through that, across that point bar and cut off that bend. But that'll get filled with sediment too, and that'll start, so you get this, even though there's a cutoff, the other channel isn't abandoned right away. By the way, while you're doing that over here, I'll create another channel over here. So much sediment, so much getting out of the way of that point bar, such weak material, you get, in this case, a real end member, and here's a little bit close-up, also, it's not all that great, is it? Kind of pixely, but I think this is the same river. You know, they don't have labels on them when you're up in an airplane. And, but you know, you can see just all these bar surfaces. Hard to tell really how much is sand and how much is gravel. But multi-threaded, braided stream. So, and then on the other side, other end, we get this, the well, let me just call it the Jarua River because I'm going to butcher Portuguese if I try. So, flowing this way, and you can see lots of old abandoned meander bends. And you know, reasonably high sediment load. I mean, that's why you can see it so nicely bright against the green forest. And if I go all the way to the Amazon's braided as heck. You know, it's got such a high sediment load that it's braiding all over the place. But a lot of these tributaries, especially since the Amazon's carrying so much sediment, you've got a rising base level essentially. So these are really low gradient, even though they're carrying a lot of suspended sediment. They don't have enough oomph to tear out that rainforest and start braiding. And instead, you get these sorts of meander patterns. This is a relatively big one. That's 34 kilometers for scale. Here's another one. This is in Colorado. This is a relatively small one. This is 270 meters per scale. Now, this is like the west of the Front Range. Yeah, west of the Front Range in Colorado. You've got essentially what do you call it? It's a basin that doesn't drain anywhere. Or if it does, it barely does. And so even though it's relatively dry, you've just got sediment getting really fine. This really low gradient stream coming into this basin. And enough vegetation is getting, you know, things are happening slowly enough. Its sediment load is small enough. So bars are building slowly enough that vegetation does have a chance to get established, and you still have that single threaded meandering characteristic. So let's make a note of, you know, before I get too far along, let's write some stuff down so we're not. So any river that's carrying, again, a substantial bed load will tend to deposit point bars and erode the opposite bank. And so if we look at these, you know, these wildly different sorts of river patterns, that is the braided on the one hand, the meandering on the other, it's all about the other factors in the system. They're still both doing this. All right. So when do we have one or the other? So what did we say? What did I say about a meandering river? Well, on some level, we've got an issue simply of, it's not all that simple, but what it kind of comes down to, and the reason that we get those highly sinuous meander forms is that the flow is weak compared to the strong floodplain surface. But let's, you know, again, review and break that down into the details, right? We've got low sediment load, and we've got fine sediment load, relatively. And essentially based on both the relatively low sediment load and how fine it is, that gives us relatively slow, well, what these two amount to, if I change this to this plus this equals lateral migration. Right? And all rivers will do it if they've got enough bedrock. So that is the channel, so-called, is changing, but it's the boundaries that are moving, right? We've got this inside of the bend part that's building out, the outside of the bend part that's eroding away, and so the channel appears to move, lateral migration. So when we have a relatively low sediment load, and what kind of goes with that is low boundary shear stress. And so we get slow migration. We get vegetation. Not sure if it's quite the right phrasing, but so vegetation grows on the floodplain, the banks tend to be vegetated, everything's held together pretty nicely and roughened up by all those green things. And hence, what we have is that effectively the material, the boundaries of the flow, either both the floodplain surface and the bank, that their strength is greater than the shear stress that the flow generally provides. So in this particular, I'll specify that floodplain strength is greater than the boundary shear stress. What's implied there is that if we're talking about floodplain strength being the relevant factor, then this boundary shear stress is the shear stress at what boundary is, again, the floodplain. We're talking overbank flow. So we've got relatively modest overbank flows that don't generate so much shear stress that typically they can overcome that strength of that floodplain material, or combination of that material and the vegetation. Also that, the fineness of the load, the fineness of the stuff that's deposited, trees and shrubs like that, right? It's easier to root and take hold in sand and silt than it is gravel and sand. Plants can do it, but, it's nicer this way. So, on the other side here, we've got braiding. Brain. Am I feeling brain dead? Is that? we're going to have a high sediment load. High, large. It's going to be relatively coarse. And we're going to have high boundary shear stresses. Now, within the channel, that means I'm going to build bars quickly, and I've got lots of oomph to erode that outer bank. So I'm going to get fast migration. And so I'm going to get unvegetated surfaces. And there may be other things other than the speed of the migration that contribute to the lack of vegetation. Maybe we're in a desert, like up in Tibet or something, you know, and it's just hard for anything to grow at that altitude, for God's sake. And, or maybe we're in Alaska, where the growing season's very short anyway. But what that's going to mean is that in this case, my boundary shear stress is going to win the boundary shear stress is going to be greater than any floodplain strength. Now there's an element of that that's counterintuitive when we talk about floodplain strength, because that floodplain is, in this case, mainly coarse material. So just in terms of the sort of shear stress it takes to pick up a particle, you know, we need more shear stress to pick up the stuff that's on this floodplain than we do the meandering one, because a lot of this is silt, really fine silt at that. However, vegetation wins, right? All that nice silt, vegetation gets nice and vigorous, and it's that vegetation that matters rather than the material itself so much. And then again, you also get some weathering of that silt and development of clays and some cohesion that develops because of that stuff. So it's not all about particle size, but so in essence then, this causes that, right? Because we've got, and when I say meandering, you know, we'll put up single threaded and over here, you know, the fact that we've got these large boundary shear stresses relative to the floodplain strength is causing the braiding. And right, also multi-threaded. You know what I mean by thread? I simply mean, you know, the thread of a channel. So one channel, many potential channels. In fact, with that intense braiding, it's hard to even say what is a channel. As you raise stage, you're going to start getting new channels as you inundate areas, and then if you raise it high enough, it's all going to become one channel. So it's kind of confusing. Now, since all channels do this, again, if they're carrying enough load, it's a basic feature of the hydraulics of carrying that sediment. And so we see, or I guess we can also infer that that is the case, that we're dealing with a fundamentally hydraulically controlled phenomenon by the fact that the Meander wavelength, that is that distance here, just the distance between subsequent crossovers in a straight line, is from such a nice functional relationship with channel width. Now it's not quite directly proportional to channel width. It's more like 1.1, channel width to the 1.1. This is a power law. And so that, you know, it doesn't mean that fundamental width, the channel width, or the width of that bankful flow is a fundamental hydraulic scale. I think it more just means that you kind of get more of that total width in the larger streams because the amount of the effect of the banks is a smaller proportion over the total. That's a bit into the weeds though. Now, we can also get some meandering in other cases where we've got strong enough material. And another way to get strong enough floodplain material to resist cutting off of those bends is just to cut down so that it becomes bedrock in the way. So this is Buffalo River in Arkansas, Buffalo National River, and the flow is coming towards us here and going away here. And I'm up on, I showed you a picture of that bluff, the one that's about 500 feet total relief, and I'm standing here in the middle of it. Now I've clearly patched together a bunch of different photos here, and I've also altered it a bit to sort of highlight this line right here of the what we call slip-off slope. But if you zoom out on this and you look at it without any scale on it, it just looks an awful lot like a normal point bar and a normal cut bank on this side. Maybe a relatively high cut bank, but then you get down into it and you realize you're talking bedrock. So bedrock meandering is a thing. Again, because all these rivers do it. This one is carrying lots of gravel. You see here. I talked about that gravel a bit last time, so a lot of it's chert. But we might expect to see some similar sort of, well, I guess just looking at this, I'll just say, you know, for the size of that river, that meander bend is relatively large. Here are just unconfined alluvial meanders here, and meander wavelength versus channel width. So here's the meander wavelength going as width to the point to about the 1.1. And here's a bunch of bedrock meandering streams up here, indicating that especially as we've got smaller, on that smaller end of those bedrock meandering streams, the effective discharge for bedrock erosion and lateral migration is a lot bigger than bank full, which isn't too surprising. I mean, you know, bank full seems to be the thing that carries the most sediment along. That doesn't mean it's the thing that carries the most boulders or does the most abrasion of hard rock or plucks out the most gravel. But those lines tend to kind of converge as you get to the very large end of the bedrock meanders, indicating that more normal-ish kinds of flows are governing that behavior. The Buffalo River is plotted with the triangles. So this reach is, I think, that point there. Now here we see that one point falls above all the rest. These fall right on the trend, one's above the rest. I believe that this has to do with massive sandstone and therefore abrasion versus cherty limestone and therefore plucking. These are migrating apparently much faster, but apparently their formative discharge is larger because it's plucking rather than abrasion. Plucking, more efficient, faster migration, but it does take larger flows to pluck rather than simply blow sand up against massive rock. At least that's my thinking. All right. In our last 5 minutes, let's talk a bit about what rivers might leave behind. This is in Kansas. I didn't know Kansas had lots of bedrock rivers, but it does. Kansas near Lawrence, near the Kansas River. And you see this big old package of sediment up here. And then sometime in the last 10,000 years, probably about 10,000 years ago, and it probably took like a minute for that river to cut down through all that soft stuff and hit the bedrock beneath. And so, if you look at, like, when we do alluvial meandering kind of studies, you'd think the Midwest is full of them, but not really. They're all in size. And so when that incision occurs, that's not the floodplain anymore. So we've had this valley fill with sediment, and then the river's cut back down. So, and that you can get multiple levels of that. And here's a terrace up here, another here, modern floodplain down here, such as it is, about that wide. These are what we call cut in fill terraces. Probably write that down. And here's a little PowerPoint animation. So you're getting these, these fillings. The stream will evacuate part of it, then fill part of it back in, and so on, and rinse and repeat. And so you can get multiple terrace levels. A lot of, some of them paired, as there's a terrace on both sides, maybe some not. Now there's another kind of terrace. When you've got your stream eroding rapidly relative to the rate at which it's down cutting into bedrock, you plane off, you bevel off that bedrock surface to a relatively flat plane. That's called a strath. And when you then cut down into that strath, you leave behind a strath terrace. And so a strath terrace is one in which a lot of, in this case, so the rising part is what we call the riser, and then the top here is the tread. And so for a strath terrace, a lot of that riser will be bedrock, with essentially one package of bottom set and top set up on top of it. And then, we can do that again and again. Now, what causes the downcutting? It could be that there are climatic events, base level fluctuations. It could also be random chance in that, rivers sweep back and forth, but they don't go regularly back to the same starting point every time. So sometimes you may see these simply as, river never got around to eroding that back out again. Perhaps no external change required. Turn on the light, you can see what I wrote. But yeah, so we've got these two sorts of terraces, both somewhat enhanced by the fact that we do this lateral migration, right? The strath terrace especially, we've got to have that rapid lateral migration to create the strath. Consider how rapid it has to be relative to this case, right? Where here we have probably lateral migration faster than vertical incision, but not a lot faster, right? In the time that it takes the river to cut down, the river moves out that much. And so we don't bevel off a big wide strath. Go out to Alluvial, you've got that wide valley. The last stop on our field trip was supposed to be Clemens Park, which has got a nice strath terrace. So that wide valley bottom in Ulce, that's a strath terrace. What's that?
I was going to ask, what was the top of
The tread. Yeah. All right, see you all next time. I'll get that quiz posted later today and put up an announcement when it's ready.